All right, so this is section 11.3, the integral test and estimations of sums. Okay. So the concept of what this section is all about is using an integral to somehow find the sum of the series. Now this is kind of a complex concept as to how do you go from one to the other. But basically what's happening here is, let's suppose we have this integral or this function here, where this is the function f of x, right, going down here, and this goes from 1 to all the way down, let's say to to infinity, right? Goes just all the way down there. Okay, so basically, say if we take the integral of this, right? Remember, because we're taking the integral, that means we're taking the area underneath this curve from 0 to infinity. Okay, and if this integral actually gives us a value itself, as it goes to infinity, eventually it will touch, in this case, 0, right? So if it finds an actual value, therefore the sum of all of these individual rectangles put together, right, the sum of all the series itself, actually converges. Okay. And that's pretty much the section is all about, is, okay, if I can find the integral of the function itself, or in this case, the integral of the series itself, and if that converges to a single value, therefore, by default, the series also converges as well. So that's kind of the concept of what's going to be happening here. If you turn the page, we actually get the actual definition of what the integral test is all about. Is suppose f is continuous, positive, decreasing function, and that's the biggest thing when it comes to the integral test. It has to be decreasing and also positive, which is the biggest of the two as well. So notice, so here it is decreasing and still positive, right? It's above the x-axis, but it's decreasing. Okay. Usually, when it comes to the integral test, it's very hard to use the integral test because that condition of you have to show it's actually decreasing the entire function itself, which is kind of a headache in general. Now, in most cases, when you do the integral test, a little hint, you'll be doing a lot of these when it has fractions, or the bottom number, or the bottom of the fraction, or the denominator has the values of n himself, or the summation of what you're dealing with itself. Okay, and that gives you kind of a hint that you can use the integral test to help you out, make it much faster to deal with. Okay, so what it says is, if it's decreasing in positive on the function from 1 to infinity, the function a sub n equal the function of n, then we have one of these two happening. If the integral from 1 to infinity of the function converges, in other words, you find a value, therefore the series also converges. If the integral from 1 to infinity of f of x, again, diverges, so goes to infinity, anything like that, then the series also diverges. Okay. Now, one very, very special test we're going to be dealing with going forward in this as well, and we talked about this a little bit in the other sections, is called the p-series test. Now, the p-series test is, if I have the sum from 1 to infinity of 1 over n to the p, this converges if p is strictly greater than 1, and diverges if p is less than or equal to 1. And you'll see how this is going to come into play. It helps us a lot, when it comes to finding if something converges or diverges, especially if you don't want to deal with the integral test itself. Okay, so let's try this out using our new type of way of finding if series converges or diverges. Okay. All right. So here we have this value here. Okay. So if we want to use the integral test, this is going to be the integral from 4 to infinity. Again, we're starting from 4 because it starts at 4 there, of this here. dn. And then we just take the integral, the old-fashioned way. So again, what I like to do is just move it to the top, so the n minus 3 to the negative 2 power dn. So this is a u substitution, right? So u equal n minus 3. du is equal to 1 dn, so that's good. So this is the same thing as integral from 4 to infinity of u to negative 2 du. All right, so take the integral. This is to be negative u to the negative 1 power. You value it at 4 infinity. All right, so now this is going to be the limit as n goes to infinity well, already took the integral, right? So, well, essentially it's basically that, right? So of u to the negative, I'll just do one more step. Kind of had a brain fart there. So that's going to be the limit as n goes to infinity of n minus 3 to the negative 1 power evaluated from 4 to infinity. And we'll just say this is n for short because we're doing that balance. Okay. So again, in this case, we're going to plug in n in here, so we have the limit as n goes to infinity of 1 over n minus 3 minus 1 over 4 minus 3. Okay. Now remember, we're taking the limit, so this actually goes to 0, and this is negative 1, so this ends up being negative 1, which is good, right? So it goes to a value, so therefore this converges. Now this is another way we could do this. So what I meant by using the p-series is you can actually skip all of this here and actually use the p-series. And this is how you're going to use it using this type of way. So what if we just rewrite this? So let's suppose, that's pretty lengthy, and that's the reason why the integral test is pretty lengthy, because, you literally have to take the integral, which is sometimes pretty difficult itself. Okay. So, but how do we use this p-series test to help us out, make it much easier to deal with? And how we do this is we're going to let x equal n minus 3. Okay. And then we're just going to substitute it in and see what we get now. So this is going to be now the sum of n equaling 4 to infinity of 1 over x squared, right? Because I just substitute that in. Well, notice that is the exact process of what we have in here, right? 1 over n to the p. In this case, n is the x value. So we can actually use the p-series test to automatically show if it converges or diverges, because we weren't asked to find the actual value itself. So therefore, our p-value is equal to 2, which is greater than 1. So therefore, by default, this converges. So by contrary, the sum of n equaling 4 to infinity of our original one also converges. Look at that, much less work, right, to deal with. But again, it's a slick way, and again, this is the reason why the p-values test is very, very powerful, because you just compare it to, there's a way to manipulate your function to look like that, and then you could just use the consequence of that p-series test. And again, you could use the integral test, but as we go in the next couple examples, they get pretty lengthy, pretty bad, because again, you have to take the integral of it. Okay. So let's try another example here. So we want the sum from n equaling 1 to infinity of natural log of n over n. Okay, so take the integral of this value. So we're going to take the integral of 1 to infinity of natural log n over n dn. Okay. All right, so let u equal natural log of n. du is equal to 1 over n. And notice that's exactly what we have here. So this ends up being integral 1 to infinity of just u du, which is going to be u squared over 2, evaluated from 0 to infinity. Okay, so this is going to be the limit as n goes to infinity of natural log of n squared over 2, evaluated from 1 to n. Okay. And now we just plug it in, right? So plug in 1, do this here. So we take the limit as n goes to infinity, plug in 1, this is natural log of 1 squared over 2 minus natural log of n squared over 2. Well, natural log of 1 is 0, so this goes away, and this actually goes to infinity, so it diverges, right? So infinity, so this actually diverges. Okay. Now, in most cases, like again, you can use the p-series. Now, you may think, how in the world do you use a p-series here to evaluate? It's natural log. It's not like it's 1 over a single value itself. Well, let's see what we can do. So let's just rewrite this real quick. Okay, so if we use the limit rule, if we take the limit and see if it actually goes to the value, right? That was the old-fashioned way of finding if a series converges, diverges back in the couple sections ago. If we take the limit as n goes to infinity of natural log of n over n, notice we have L'Hopital's. This is infinity over infinity. So if we use L'Hopital's rule and take the derivative of each one, derivative of this is just 1 over n, derivative of n is just 1. Well, this is just the limit as n goes to infinity of 1 over n. Notice that's the p-series. So, according to the p-series, this also diverges. In this case, it's the first power, right? So p is equal to 1. So it diverges because it equals 1. So there's multiple ways to actually manipulate it in a way to use a p-series to help each other out. So very interesting topic, right? That's why the p-series test is very, very powerful in that case. All right, let's try one more down here. You can kind of tell where I'm going to go here, right, as well. All right, so take the integral of 1 to infinity of 1 over 3n minus 1 to the 4th power dn. Right, take the integral, so let u equal 3n minus 1, du is 3 dn, so divide it over, so we get 1/3 du is equal to 1 dn. So this ends up being integral from 1 to infinity. I'll just put the 1/3 out here of u to the negative 4th power. Okay. All right, so keep going. So we get u to the negative 3 over negative 3. And evaluate from 1 to infinity, and the 1/3 is still out there. Okay. All right, so let's see what we get. So we can take the limit as n goes to infinity of 1 over 9, negative 1 over 9 of 3n minus 1 to the 3rd power. Evaluate at 1 and infinity. Okay. Keep going. So this is going to be the limit as n goes to infinity of infinity, right? So just plug it in. So I'll just say this, sorry, this is going to be n of negative 1 over 9, 3n minus 1 to the 3rd, plus, it goes negative is positive, or just exactly that. 9 times 3 minus 1 to the 3rd power. Okay. Now remember, this also goes to 0, right? This, it's 1 over it, so this goes to 0. So essentially, this ends up being given a value, right? So this just plug it in. So what's this? 3 minus 1 is 2. 2 to the 3rd is 8. 8 times 9 is 72. So this is just 1 over 72, which is a value. That's going to be the L. So therefore, this converges. There we go. Now, if you want to, well, can we just use the p-value series? Yes, you can. The exact same template I showed you guys in part 8. We'll just let 3n minus 1 equal x, and you compare it to the p-series, so therefore it also converges by the same process, right? Because in this case, p is going to be 4, and notice you get the same result because they won't contradict each other. So again, integral test is, pretty much of a pain sometimes, but unfortunately sometimes you have no choice to do it. But one way around it, or you could have it run one way around it, is using the p-series test to do so, or in a way somehow manipulate it in a way that you actually see it's actually that particular value. But again, like for the example, this one's a pretty tough one to see how you would go in about doing the p-series test. So the integral test would be the way to go and do that kind of stuff.